Hello, my name is Mr. Asprey, the Maths YouTuber with 3 objectives this year. Number 1 is to help you get the best maths grade possible in your A-level. Number 2 is to reach 50,000 subscribers on YouTube. And number 3 is to throw over 100 180s in darts. Now, number 3 you probably can't help me with. Number 2 you definitely can by subscribing to my channel. Click that button right now. And number 1, well, you've already started watching this video, so you're definitely going to help you get the best maths grade possible. Brilliant. Let's get into this paper, which I think is quite a tricky one. 2024 Pure Maths 1 EDEXCEL A-Level. Let's get into it. Question number 1, and we have g of x is equal to this cubic expression, where k is a constant. It says given that x minus 3 is a factor of g of x, find the value of k. Okay, so we're going to use the factor theorem here, and the factor theorem states that if we know that x minus a is a factor of, let's say, f of x, then it is implied, and implied by, that f of a will equal 0. So in this case, we've got x minus 3 is a factor of g of x, so that tells us that g of 3 should equal 0. And to find g of 3, we just substitute 3 into this function here. So I'm going to write 3 lots of x, I'm going to replace with a 3 cubed minus 20, 3 squared plus, and let's just expand this out. So k times x, but x is 3, so that's just going to be 3k. And then 17 times x, when x is 3, is going to give me 17 times 3, which is 51, and then plus k, and we've said that equals 0. Okay, let's evaluate this. So 3 cubed is 27, times 3 is 81, 3 squared is 9, times 20 is 180. Very good. And then we've got 3k, and then plus 51, and then plus k equals 0. Okay, let's collect up the k's. We've got 4k there, and then here we have, why not, let's just use the calculatrice here. We've got 81 minus 180 plus 51 to give us minus 48. So minus 48 equals 0. So we get that 4k is equal to 48. Divide by 4, k is equal to 12. Job done. Box it up. 3 marks. Let's move on to the next question. Okay, question 2. It says find in ascending powers of x the first 4 terms of this binomial expansion. So first thing to notice is that we have a fractional power, which means we're going to need to use the formula for the binomial expansion that we can use with any given power. That is in our formula book, and it looks exactly like this. Okay, so we're going to use that. Next thing to note is that the formula from the formula booklet here needs to have 1 as the constant term inside the bracket. We already have that, so that's good. It means we're not going to need to take out a factor. Okay, so we can just go really, and so the power n is going to be a half, and this x here is in fact minus 9x. So I'm going to do a little bit of bad maths here, but say like x essentially equals minus 9x. Okay, so let's use this formula then. So we start off with, I can say that 1 minus 9x to the power of a half is equal to, or in fact, technically I should say approximately equal to, because we're not going to give all the terms, we're just going to give the first 4. So the first term here is 1, yep, good. The next one is n times x. So n, we say, is a half, and x is in fact minus 9x. Okay, great. Right, next term is n times n minus 1. So n again is a half. So we'll do a half times by a half minus 1, which is minus a half. And that's all over 1 times 2, which is 2. and then x squared. Now this is where people make a mistake. When we have x squared, we have to take the new x, which is minus 9x, and we've got to square it like that. Okay, and we need one more term. So the next one in the series is going to be n minus 1, and then n minus 2, which will be minus 3 over 2. And that's going to be all over 3 factorial, which is 1 times 2 times 3, which is 6. And then we're going to have to do minus 9x, and this times the power of 3. Okay, great. So all we need to do now is just evaluate these. So this is going to be minus 9 over 2x. This one will be a bit tricky. I probably should use a calculator for this, but actually I'm going to risk it. We've got a half times a half, which is a quarter, times divided by 2, which is an eighth. There's going to be a minus there, and then we're going to have to times that by the 9 squared, which is 81. So it's going to be 81 over 8, and that would be x squared. Ooh, you know what? I'm just going to use the calculator for this one. Okay, so I've typed it all into the calculator exactly how I would do in an exam. Pressed execute, and we've got ourselves minus 729 over 16, and that is going to be x cubed, because of course the x here is going to get cubed. Okay, perfect. So let's go on to the next one, and it says give a reason why x is equal to minus 2 over 9 should not be used in the expansion. Okay, so there's an important rule in when you use the binomial expansion, and that is that we are valid for the modulus of whatever the x is, which in this case is minus 9, needs to always be less than 1. So, well, the modulus is going to take care of the minus sign there, and if we divide through by if we're going to divide through by 9, we're going to get that the modulus of x needs to be less than 1 over 9. Okay, so in this case, x equals minus 2 over 9 is outside of the range of validity. Outside of range of validity. I think I'm saying that right. Okay, perfect. Yes, so because yeah, so the smallest x can be, so basically what this means is when the modulus is less than a ninth, it means that x needs to be in between minus a ninth and positive a ninth. So minus 2 ninths is too negative here. It's outside of this range that we need, so therefore it's not going to be used for an approximation. Question 3, we've got a function here, and x is given in radians, which is important, as you can see from the domain over here. And then it says that given that the equation f of x has a single root, show that that root alpha lies within this interval. Okay, so this is classic change of sign. If you want to show that a root lies within an interval, we have to substitute the endpoints of that interval into the function and show that there is a change of sign. So I will just go over to my calculator. Okay, and I've subbed it in, and I've made sure that I'm in radian mode, which is extremely important here. Okay, so that is the value that we've got. So that is going to go down for this one here. So you need to write this down just to show you're working. Okay, that should do. And then go back to the calculator and just change this now to a 3.7, and just make sure you change this one as well to 3.7, and then that gets written down here. That's fine. Okay, and then we say there is a change of sign, and f of x is continuous on the interval, and then we can say therefore there is at least one root find the derivative function. No problem. So f dash of x, when I differentiate x I get 1, and when I differentiate tan it goes to sec squared, but by the chain rule, because the input is a half x, I need to multiply by the derivative of the input. So the derivative of a half x is a half, so I'm going to multiply by a half. Tan differentiates to sec squared, and that input stays the same. So by the chain rule we have 1 plus half sec squared a half x. Okay, great. Part C. It says, using 3.7 as a first approximation for alpha, apply the Newton-Raphson method once to obtain a second. Okay, so let's find the Newton-Raphson formula. Okay, and there we have it. That's straight out the formula booklet. So what this tells us is, if we are starting with 3.7 as we were told, then the next x value will be the previous x value minus f of that x value over the derivative at that x value. So what we're looking for then is going to be 3.7 minus the original function sub in 3.7 over the derivative function sub in 3.7, which will be 3.7 minus, now the original function was x plus tan a half x, so we want x plus tan a half of x all over the derivative function, which is right here, which is 1 plus a half sec squared and then a half times by x. Okay, so that just needs to go into our calculator. It's going to be quite tricky to type it in. Let me show you how I'm going to do it. Okay, so we're going to do 3.7 and we're going to go minus and we're going to go bracket and we're going to go 3.7 plus tan of a half times by 3.7 close bracket. Okay, that was the easy part. Now go down to the line below and we're going to go 1 plus a half multiplied by, now sec squared is 1 over cos squared, so we're going to do 1 over cos and we're going to do a half times by 3.7 and we're going to close that bracket, and then what we're going to do, we need to square that in fact, so we need to put a bracket here and a square and go back over here to close that bracket. Okay, that should be good. That should be good. We press execute and we get a value. Fantastic. Okay, so that is 3.67 and it's asking us to go to 3 decimal places, so we get this 3.672. Okay, lovely, and that is the correct answer, so we are good. Okay, question number 4. It says, given that y is equal to x squared, use differentiation from first principles. No problem, but we need the formula for first principles. So we go to our formula booklet, because it's given in the formula booklet. There it is. So we can write f dash of x is equal to the limit as h tends to 0 of, so f of x plus h. Well, let's write that over here. If f of x is equal to x squared, then f of x plus h is equal to x plus h squared, which, when we expand this bracket out, we will get x squared, we will get an xh and another xh, so we'll get 2xh, and we'll get h squared. So our fraction now will look like f of x plus h is going to be x squared plus 2xh plus h squared, and then minus f of x, which we know is x squared, all over h. Okay, great. So I'm going to write equals, and I'm going to go limit as h tends to 0, and then we're going to sort this fraction out. First thing we're going to do is this will cancel with this, so we'll get 2xh plus h squared over h, and now we can divide through by this h, so we're going to get just 2x plus h, like so. Okay, great. Now what we're going to say is we're going to say that as h tends to 0, comma, 2x plus h is going to tend to 2x. So therefore, f dash of x is equal to 2x. So h tends to 0, of course, what we have inside this bracket, with h going to 0, it's just going to leave us with 2x. So when we apply the limit, we just get left with 2x. So f dash of x is equal to 2x. Beautiful. There's the final answer. Thank you very much. Question 5, it says the function is defined by f of x is equal to a fraction, essentially. So when it's asked us to find the derivative, we need to think of the quotient rule, because that helps us differentiate fractions. Now I'm going to go to the formula booklet, and here is the quotient rule. Now, I don't really like it in this form. I don't know why they give it as a function. I think I much prefer it when you have u and v, then the derivative, the dy by dx of this will be capital V du by dx minus capital U dv by dx all over v squared. I think that's what most people are used to with the quotient rule. So let's define our u and our v. Well, u is the numerator of the fraction and v is the denominator. So u in this case is 2x minus 3, and v in this case is x squared plus 4. So du by dx, we'll just differentiate u, and 2x differentiates to 2, and dv by dx, we differentiate this, 2 comes down, so it's 2, drop the power down by 1, x to the 1, so it's just 2x, and a constant term differentiates to 0. Okay, so we've got everything we need, so now we can actually differentiate this function f of x, so we can say f dash of x is equal to, and the formula is v, so in this case v is x squared plus 4 times by du by dx, which is 2, minus u, which is 2x minus 3, times by dv by dx, which is 2x, and then that is all divided by v squared, which will be x squared plus 4 all squared. Okay, great. So now we just need to simplify the top. We're going to get 2x squared plus 8. This is going to be minus 4x squared, and then the minus and the minus turn to a plus. So when I times this 3 by 2x, we're just going to get plus 6x. Again, all over x squared plus 4 all squared, to give us a final answer of just write it here, save space, minus 2x squared plus 6x plus 8 all over x squared plus 4 all squared. Okay, it says where a, b and c are constants to be found. I don't think we need to write it out, but I will do just because I'm paranoid. So a is equal to minus 2, b is equal to 6, and c will be equal to 8. And that will be our final answer. Okay, great. Now what does the question ask? It says, hence use algebra to find the values of x for which f is decreasing. Okay, so if f is decreasing, it means that it's sloping downwards, which means that its derivative is less than 0. So we need to find when the derivative is less than 0. Okay, so for part B, we need to find when minus 2x squared plus 6x plus 8 all over x squared plus 4 squared is less than 0. Now we have to think about this carefully. When a fraction is negative, it happens either if the numerator is positive and the denominator is negative, or the numerator is negative and the denominator is positive. If they're both negative or both positive, then the overall value of the fraction will be positive. Now we know for certain that the denominator is always positive because it's a square, it's been bracketed and then it's been squared, so it's always going to be positive. So we need this numerator to be negative. So essentially we just need to solve that this part, we need this bit to be negative, so less than 0. Okay, I'm going to times through by minus a half to get rid of the minus sign by the x squared, and also everything's got a factor of 2, so we can get rid of that. So it's going to be positive x squared minus 3x minus 4, and if we times through by negative, we've had to swap the sign over, as what we do when we times or divide by negative in an inequality. We have to swap the sign over. Okay, this can be factorised, I'm sure, and this is going to give us our critical values of this quadratic inequality. So those critical values are x equals 4 and x equals minus 1. So if I were to sketch this quadratic, then it would go through minus 1 and it would go through 4. So it looks something like that, minus 1 and 4. And if we need to know where this quadratic is greater than 0, well, it's this part here and it's this part here. So the x values that give us those parts of the graph are when x is less than minus 1 or when x is greater than 4. So our answer is, does it ask for set notation? No, it doesn't ask for set notation, it just says find the values. But anyway, I'm just going to give it as a set. I'm going to say that x needs to be less than minus 1, union x needs to be greater than 4. And that should do the job. Perfect. Question 6, and we have a sketch of a modulus function. We get given the equation. It says that the vertex of the graph is at point P, so that's like the minimum point of this modulus function. Now in order to minimise the modulus function, well, this part can only be positive or 0, so the smallest possible thing we can have is 0, and the value of x which makes that 0 is 2. So we know then for part A, we want x to equal 2 to get to the minimum point. And when that is 0, then we've just got y is equal to 0 plus 5, so therefore y is equal to 5 at that point. Which means that the point P is at 2, 5. Which is quite nice for 2 marks. Okay, great. Right, on to the next one, part B. And it just says solve this equation. Now these can be really tricky, I find, because there may be two solutions or there may be one solution. So what I like to do is take this part of the modulus function, the graph of it, and just kind of extend it on. And that's that has positive gradient. So if I was to solve an equation, the modulus part I would keep as x minus 2. I would keep it exactly how it is to give a positive gradient, so 3x. Now this one here, I'll extend this one out as well. And that one is where the graph has been flipped. So there, in order to get that flipping, we have to make the modulus part negative. So you could do minus x plus 2 instead if you're solving the equation. Okay, so let's see how many times this line here crosses. Now, to note, if I was to draw this line on, the line of y is equal to 16 minus 4x, it would have a steeper gradient than the modulus sketch, because that one has a gradient of 3, whereas this one has a gradient of 4. You know, give and take. It's given it's minus, but you know the value of it, the magnitude of it is 4, so it's going to be steeper. Now it's going to cross here at 16. So it's also important to find where the modulus function crosses the y-axis. Well, when x is 0, we're going to get minus 2 is going to turn to 2 because of the modulus, times 3 is 6, plus 5 is 11. So it's going to go through there at 11. And this one here is obviously going to go through at 16 because that's the y-intercept. It's going to go through the x-axis at, when y is 0, we're going to get 16 minus 4x. So 4x equals 16, so x equals 4. So it's going to go through, and we know this point here is at 2, so it's going to go through here at 4. Right, great. Now this may seem like a bit of a faff to do all this stuff, but I like it because it just gives me real clarity as to how many solutions I'm going to be expecting. Right, so we're going to get one solution here, which is good. That's a good solution because that is actually on the V shape. And we're going to get one down here, which is going to be like a ghost solution. Okay, that one we don't want. Okay, that is not actually on the graph. So the one that we want is on the blue, and that is when we just keep the bracket, the modulus bracket, exactly the same when we solve. The one we don't want is when we flip the modulus around to negative. Okay. So after all that, it means all we need to do is just solve this equation with the bracket just normal. Okay, so 16 minus 4x is equal to 3x minus 6 plus 5. 16 minus 4x is equal to 3x minus 1. Add the 4x to this side to get 7x. Add the 1 to that side to get 17. So x is equal to 17 over 7 for our final and only answer. Okay. Next, part C. We've got a line here with a gradient unknown, but we know the y-intercept, and that line intersects the modulus functions graph at two distinct points. Find the range of values of k. Okay, so once again we've got to get back up here, and we've got to look at this graph. Okay, so what we know is that goes for 11. We know that the minimum point is at 5, and we were told that this line here has an intercept of 4. So it's going to be somewhere like that. So the first thing I'm going to do is I'm going to draw the line that cuts through the vertex. Okay, so let's find out this green line. Let's just call it line 1. That's going to be important. Let's just find out the gradient of it first. Okay, so I'm just going to go here, part C, and I'm going to work out that particular gradient. Now that gradient was point P and the point 0, 4. So we'll do 5 minus 4 over 2 minus 0. So this is going to give us a gradient of a half. Okay, so this line here has a gradient of a half. Now this doesn't intersect at two distinct points, it intersects at one point. But if we were to increase the gradient, then it would start intercepting at 2 points, like there. You can see that intercepts twice. So if we increase it from above a half, it's going to intercept twice, apart from when we get to a certain gradient, when it will be parallel to this line here, and that's where it will stop intersecting twice. So that gradient is the same gradient as the modulus function, so that has a gradient of 3. Okay, so just anywhere in between those two and it's going to intersect twice. Outside of that, it won't intersect twice. And also, just thinking about a negative, if you had a really steep negative that had to go through that y-intercept, then that would only intersect once as well. Let's just quickly show you what that would look like. It would go like this, and you can see it's only going to intersect once, so negative gradients aren't going to work here. Okay, so I think all we need to do here is just state now that the range of values of k are such that, I'll give it intercept notation, just we don't need to, but I think it's just good habits to do it for all ranges. Like this and like this. Also important to note, it can't equal because when it equals a half, it only cuts at the vertex, which is 1 point, so that's no good. And when it equals 3, it's parallel, so again, that's no good. It only intersects once. So that is our final answer. Gosh. Okay, we have for number 7 a cylindrical tank, height 1.5 meters. Initially the tank of water is full, that's important. So what this tells us is that when t equals 0, the height is equal to 1.5. Then water starts leaking out. While the tank is leaking, the depth of water is modelled by this differential equation, where t is in hours, that's important, that might be useful, and h is in meters. Use the model to show that. Okay, so essentially we've just got to solve this differential equation. Okay, so let me just write it out here. So dh by dt is equal to minus 0.12 e to the minus 0.2t. So we're going to separate the variables here. We're just going to multiply both sides by dt to get this. Like so, and then we're just going to integrate both sides, like so. Okay, so the integral of dh is just h, and here when we integrate an e function, we just keep the e function exactly the same, but we just divide by the derivative of the input. So we need to divide by the derivative of minus 0.2t, which is just minus 0.2. And of course we're going to get a plus c coming along for the ride. Okay, so I need to do that, don't I? I need to do, well, the two minuses will cancel out, so really I just need to do 0.12 divided by 0.2. And we get 3 over 5. Great. So 3 over 5 e to the minus 0.2 t plus c. Is that what they want? Right, so we found a, that's the 3 over 5. B, the constant of integration, we need an initial, or we need a bit of information in order to find that. And that's going to come from right here. So we need to sub that in, and that's going to allow us to find that missing constant. Okay, so we have that t is equal to 0, h is equal to 1.5. So we're going to use that, sub it into our equation we've just formed. So 1.5 is equal to 3/5 e to the minus 0.2 times by t, which is 0, plus c. So 1.5 and equals 3 over 5. And then e to the 0 is just 1, so just plus c, sorry. And that's 0.6. Take it away from 1.5 gives us 0.9. So our final equation, which is always important to state your final equation, 3/5. I'm going to write that as a decimal because it's all in decimals. So and then minus 0.2 t, and then plus 0.9, and that's good. So if it asks you to find and show an equation, you must actually write the equation out at the end. Okay, let's go up and look at B, where it says find the time taken for the depth of the water to decrease to 1.2. Give your answer in hours and minutes to the nearest minute. Okay, so we just want the height of the water to equal 1.2. So we're just going to say h equals 1.2, and of course that's also equal to 0.6 e to the minus 0.2 t plus 0.9. So minusing 0.9 from both sides is going to give us this. Then dividing by 0.6 is going to give us 0.5. And then we're going to take the natural logarithm of both sides, which is going to cancel out the e to the power of and just leave whatever the power is, like so. And then we are just going to, well, we're just going to divide through by minus 0.2. It wants it in hours and minutes, so we need to actually find the value of this. So new calculator, not as comfortable with it as the old one, but you've got to get with the times. Okay, right, there we go. So 3.466. Okay, so what we're going to do actually, because it wants it in hours and minutes, we're going to take away 3, like that, because of course that 3 represents 3 hours, and what's left over is minutes, so we're going to times that by 60 to get the exact number of minutes. So that is 28 minutes essentially, because that's pretty close to 28, so I'm pretty sure that's all good. Lovely. Okay, let's go up, and now it says in the long term the water level in the tank falls to the same height as the hole. Find according to the model the height of the hole. So the key part here is in the long term. So what we can do is we can sub in a large value for t and see what it tends to. Right, so we've got our equation for h here, so I'm just going to write that down again. Actually I don't need to, sorry, it's in the red box, isn't it? Yeah, so that's our equation for h. So what we're going to do is we're just going to say what happens when t tends to a large number. Well, h is going to equal 0.6 times by e to a large number, to a large minus number, should I say, because it's going to be 0.2 times by a large number, but there's that minus there. So where e to a large negative number is going to tend to 0, so therefore this is just going to give us 0.9, and that's meters. And that's it. That's the final answer for that particular question. Again, you could just sub in a large number into your calculator into the formula and you'll get 0.9. Question 8, we've got the functions f and g are defined as follows. Find f of g of 2. So a composite function means you put 2 into g and then you put that value into f. So we're going to start off by putting 2 into g, which is going to give us 5 over 2 lots of 2 minus 9, which is the same as 5 over 4 minus 9 is minus 5, so that's just going to give us minus 1. Okay, so now we put that value into f. So if for us to find f of g of 2, we just put minus 1 into f, because that's what g of 2 is. Okay, so f is to 4 minus 3x squared. So we're doing 4 minus 3, and the new value to x we're subbing in is minus 1 squared. Okay, so this is the same as 4 minus 3, because minus 1 squared is 1, so that's just equal to 1. So there we have it. 1. Okay, so that was A, so this one is B. So B asks us to find the inverse function of G. Okay, so what we do is we set it equal to y, swap the x and y over, which inverts the function, and then we rearrange again for y. So we say y equals 5 over 2x minus 9. We then do that transpose where we swap the x for y, which inverts the function. And then we need to make y the subject again. So we're going to multiply up by that denominator, like so. We're going to expand out the brackets, and then we're going to make y the subject again. So we're going to add 9x to that side. Then we're going to divide through by 2x, and this is going to give us y as the subject. So 5 plus 9x over 2x. And then we're going to write g to the minus 1 of x is equal to this, 5 plus 9x over 2x. Okay, but, and it's a big one, you have to state the domain when you create a new function. So I've created an inverse function here, we have to state the domain. Now, I can see straight away that the domain is going to be that we can't divide by 0, because so therefore x can't be 0. So I'm going to write here, comma, x can't be 0. Also, another way of doing it is that the domain of the inverse is the same as the range of the original function. Okay, and this function here can spit out any value at all. The only value it can't spit out is 0, because if you have 5 divided by a variable like this, and if you wanted that to be 0, there's just no x value that can make it. You multiply up and it will just make nonsense. It'd be 5 equals 0. So 0 is the only thing which cannot come out of this function. So therefore it's the only thing that cannot go in to the inverse function. Brilliant. Okay, now we're asked to find g of f of x, which means I pick up the whole of f of x and I put it into g. Okay, so let's do that. Just going to box this up. That's the final answer. And we're going to go down here and we're going to try and do g of f of x. Yes. Okay, so to do g of f of x, I need to write out g, but when I get to an input, I replace it with f of x completely. So I start by writing out g, but I've got to an input of x, and what I do is I'm inputting f of x into g, so I need to put that input now as the whole of f of x, like that, and then minus 9, because of this minus 9 here. Okay, great. So all this requires us to do now is just to simplify this. So expanding out the brackets gives me 8 minus 6x squared and then minus 9. So this gives us 5 over minus 6x squared, and then 8 minus 9 is minus 1. And I believe that is our answer for that composite function. Okay, but this comes in 2 parts. It says once you've got it, simplified fraction, done that. Now it says deduce the range of g of f of x. Oh gosh, okay, this is going to take some explaining. So part 2, let's find the range. First thing I'm going to do actually is I'm going to rewrite this function. So it's just going to make understanding slightly easier. I'm just going to times top and bottom by minus 1. So that doesn't change the function, it just writes it slightly differently. So we're going to get this. Okay, now I've done this because now hopefully it's easier to see that the output of this function will always be negative, because you've got a minus here, so the top's definitely negative, and the bottom is always going to be positive, because you know x squared always gives out positive values, so we're always going to get a positive on the bottom, so overall we're going to get a negative. Okay, so we know all of our values are going to be negative. Now, what's the biggest value it could possibly be then? Perhaps it could be 0. Well, no, it can't be 0. We can't solve this equation. There's no value of x that you could put on the bottom here that's going to make this give out 0. So you can't divide 5 or minus 5 by something and get 0. It just doesn't work. Okay, so we know it's negative and we know it's not 0. So first guesses really is that it's going to be like less than 0, but perhaps there is there's a lower bound. Perhaps there is the like the largest negative number. Well, let's look at the bottom here and think about if I want to get like the biggest negative value, I would need the denominator to be as small as possible, because if you divide by a smaller number you get a bigger value. So what's the smallest this could possibly be? Well, x squared is always positive, so the smallest it could be is 0, and that would leave just 1 on the bottom, which would give us minus 5 over 1, which gives us minus 5. So that's the smallest it could possibly be. So like the biggest negative number it could be is minus 5, and it can equal that. So it looks like it's trapped in between minus 5 and 0, so that is our range. Perfect. Okay, let's do question D now. It says find the range of values of k is a constant, for which the equation f of x equals h of x, which is this guy, has no real solutions. Okay, so I'm thinking no real solutions means we're going to have to use the discriminant, and it's asking us to solve f of x is equal to h of x, which is going to give 4 minus 3x squared is equal to 2x squared minus 6x plus k. Let's bring it all over to one side. So add the 3x squared and minus the 4. So it equals 0. So now if we want no real roots, then this means that the b squared minus 4ac needs to be less than 0. So the b term is the coefficient of the x. So we're going to take that and we're going to square it, minus 4 lots of the a term, which is the coefficient of the x squared, which is 5, and then multiplied by the c term, which is the constant term, which is k minus 4. So k minus 4, and we need that to be less than 0. So that's 36, and that is minus 20. So minus 4 times 5 is minus 20, times by k gives us minus 20k, and then minus 20 times by minus 4 is plus 80, like so. Okay, so minus 20k is less than minus 80 minus 36 is minus 116, and then divide through by minus 20, which flips the sign over, and we get 116 over 20 is 29 over 5. Perfect. That was a beast question, but it's done. Okay, we've got the first 3 terms of a geometric sequence. So that means if it's a geometric sequence, then to get from the first term to the second, you have to times by the common ratio, and to get from the second to the third, you have to times by the common ratio as well. Okay, actually before we get started, you can see that all of these are powers of 3, so it'd be useful to turn this one into a power of 3 by writing it as 3 squared 7 minus 2k, and then using the indices rule that a to the m to the n is equal to a to the m times n. So just multiplying through, we're going to get 3 to the 14 minus 4k. Okay, so if I wanted to work out r, well, because the first term times by r equals the second, to find r, I just do the second term divided by the first. So the second term is this guy here, which we've said is the same as this. So we're going to write that out, and then we're going to divide it by the first term, and that's going to give us r, like so. But also, r is as well, you can find that by doing, well, the second term times r gives us the third term. So to find r, we can do the third divided by the second. So that would be 3 to the 2k minus 1 over the second term, which again is the same as this, 3 to the 14 minus 4k. Here we can just multiply the brackets, so that's 2k minus 2. So might as well just write it like that. 2k minus 2. And then, so both sides of this equation, we've got 3's with powers, and we're dividing the 3's. So when you divide 3's, we're going to use this indices rule, which subtracts the powers when you divide and the bases are the same. So subtracting the powers, we will get, oh gosh, minus 4k is minus 8k, and 14 minus minus 5 is 19. Over here on this side, we're going to do the same. 2k minus minus 4k is 6k. Minus 2 minus 14 is minus 16. Great. And now, because both sides of the equation are 3 to the power of something equals 3 to the power of something, well, those two somethings must be the same. So minus 8k plus 19 is equal to 6k minus 16. Add 8k to that side, add 16 to that side, and then finally divide through by 14, and that's going to give us k is equal to 35 over 14, which is the same as, of course, 5 over 2 for our final answer. Brilliant. Okay, next one says, hence find the sum to infinity of the geometric sequence. Well, if we know that k is equal to 5 over 2, we can actually work out each of these terms, which I think is going to be quite helpful. So the first one, 5 over 2 times 4 is 10, minus 5 is 5. So the first one is 3 to the 5. The next one is, using this one here, 3 to the 14, so 5 over 2 times 4 is again 10, so it's 14 minus 10, so it's 3 to the 4. And this one, which should be 3 to the 3 if it all has worked out nicely, when expanded gives us this. 2k, when k is 5 over 2, is 5, minus 2 is 3, so great, it's 3 to the 3. Okay, so the common ratio, clearly we have to multiply by a third in order to decrease the power by 3, decrease a power of 3 each time. And the first term is this, and the common ratio is this, so we should be good to go. So part B, the first term was 3 to the power of 5, and the common ratio was 1/3. The sum to infinity formula is A over 1 minus R. So this will be 3 to the 5 over 1 minus a third. which is going to give us, calculator can help us out here, 3 to the 5, and then divided by 1 minus a third is 2/3. Okay, great. 729 over 2 for our final answer. Question 10, and we have a lovely sketch of part of this curve here, and it says that the curve crosses the x-axis at the point A. Verify that the x-coordinate of A is 4. Well, verify is very different to show that. It means that we can use the information to verify that it's correct. So we can use the fact that x is equal to 4. So we're just going to substitute x is equal to 4 into this function, and then a, you can see here at a, clearly that's on the x-axis, so y equals 0 there. So if we sub in x equals 4, we should get y is equal to 0. So that's exactly what we're going to do. So we're going to say x is equal to 4, and that implies that y will equal 8 lots of 4 minus 4 to the power of 5 over 2. So 8 lots of 4 is 32. 4, so this 2 on the denominator of the power means to root, and the root of 4 is 2, and then we take it to the power of 5, and 2 to the power of 5 is 32. So it's 32 minus 32, which equals 0, and then always want a conclusory statement, so we can say hence the hence the A coordinate is at the point 4, 0. Perfect, that does the job. Okay, right, now on to the next part. It says that the line L1 is the tangent to the curve at A. Use calculus to show that the line is given as this. Okay, so what we're going to do, use calculus means we're going to take this equation here and we're going to differentiate it, because that is going to give us the gradient function. So we're going to take this thing here and we're going to differentiate it to start with. So we're going to say that dy by dx is equal to, well, this is 8x to the 1. 1 comes down times by the 8, and then we drop the power down by 1. And obviously x to the 0 is just 1, so we don't need to write that. How do we differentiate this? Right, the power comes down, so it becomes 5 over 2x, and then we drop the power down by 1, so that becomes 3 over 2. Now we are trying to find the tangent at A, and we know that at A we have the coordinate 4, 0. So the tangent at A has the same gradient as the curve at A. So we want to find dy by dx when x is equal to 4. So sub 4 into this. So we get 8 minus 5 over 2, 4 to the power 3 over 2. So this is going to be equal to 8 minus and 4 rooted will give us 2, then to the power of 3 will give us 8, then divided by 2 will give us 4, then times by 5 will give us 20. Okay, so therefore the gradient is minus 12. And now we can just bring it all together by saying that y minus y1 is equal to mx minus x1, and just sub in a point and the gradient, and that will have the straight line. So the point has to be on the line, which is obviously the point A. So we're just going to sub in for y0, for y1 as 0, and for x1 as 4, and for the gradient m as 12. Like so. So this gives y is equal to minus 12x, and then that will give us plus 48. And I think that is as required. They want it like this, with the variables on the left and then the constant on the right. So that's fine, we can just do 12x plus y, just add 12x to the other side, is equal to 48. And that is the equation of the tangent at A. Perfect. Okay, now it says that the line L2 has the equation y is equal to 8x, and we're asking to work out by integration the area of R. Okay, so we're going to split this area up into two shapes. We have a triangle, which I'm going to colour in purple or red. And then we're going to have the area under this curve, which I'm going to colour in blue. Okay, well, sorry, I'm going to outline the triangle in red and I'm going to colour in the area under the curve in blue. Okay, so the triangle, we need to work out, let's work out this first. Now the distance from the origin to A is 4 units, because we know that A is the point 40. So really what we need now is we need the height of the triangle to work out its area. So this point here, let's call this point, I don't know, C. We need to work out what this point is, and that's where the two lines intersect. So let's go and work out where the two lines intersect. So for part C, we want 12x plus y is equal to 48. We want that to intersect with the other line, which was y is equal to 8x. So we're just going to solve this simultaneously, and the easiest way to do that here is just substitute this in here for y. So 12x plus y, we're going to sub in here 8x, and that's equal to 48, which is going to give us 20x is equal to 48. So x is equal to 48 over 20, which is the same as 12 over 3. No, it's not. What am I thinking? Sorry. 12 over 5, which is 2.4. Okay, so that's the x-coordinate of the point C, but actually what I really need is the y-coordinate, because that's going to be the height of the triangle. So the y-coordinate, we can just sub into any one of these two. I'm going to sub into this one, so it's 8 multiplied by the x-coordinate, like so, which is going to give us, I should be able to do that, but why can't let's just do it on the calculator. 96 over 5, fine, that will do. 96 over 5. Okay, right, let's go back up and show what that means. Right, so the y coordinate was 96 over 5. So the area of this triangle, which has a base of 4 and it has a height of 96 over 5, so the area will equal a half base times by height, like so. So we just need to multiply this by a half of 4, which is 2. So okay, there we go. There's the triangle, which is 92 over 5. Okay, well let's bag that up because we're going to use that in a bit. So what is missing from the triangle to make the shaded region R? Well, it's the shaded blue area. Okay, so this shaded blue area we're going to find using integrations. We're going to integrate this curve between the limits of x is 0 and x is 4. Okay, so let's do that. Okay, so I need to just grab this because that's what we're going to be integrating, and just plonk it over here. Okay, so I need to be integrating between the limits of 4 and 0, 8x minus x to the 5 over 2 with respect to x. Okay, well, how do we integrate? Well, we take the power and we up it by 1, and then we divide by the new power. And here we're going to take the power and we're going to up it by 1. Get 7 over 2, and then we're going to divide by that power, which is the same as timesing by 2 over 7. Okay, and that's between 4 and 0. Okay, great. Now we just need to sub this into our calculator. Okay, which I've just done, and that gives us 92 over 7. Great. So the region R is the triangle minus the the sort of curved area, the curved blue area. So the triangle was 92 over 5. So it's 92 over 5 minus 92 over 7, which is the curved area, the curved blue area. Okay, so that just goes into a calculator. 92 over 5 minus 92 over 7. And that is the exact area of 384 over 35. Brilliant. Question 11, and we have a semicircle which has a diameter of 10. So I'm just going to say that from here to here is 5. And it says that OB is the arc of a circle centered at A. Okay, so there's a arc here centered at A, which means that this arc has a radius of also 5, and it then just says find the exact area of R. Okay, so how are we going to start here? Well, I tell you what we're going to do is we're going to work out the area of the semicircle. That seems like a good place to start. So the whole semicircle, so the whole shape here is going to be a half, because it's a semicircle, pi multiplied by r squared, and the semicircle has a radius of 5, so 5 squared, which gives us 25 over 2 pi. Okay, so now we need to figure out this blank area here in order to take it away from the semicircle to leave us with R. So, so A to B, if I draw a line from A to B, then because B to O is the arc of a circle centered at A, it means that A to B and A to O must be the same distance, so that is also 5. Okay, and also I can draw a line from B to O, and because the B is on the semicircle, which is centered at O, which has a radius of 5, it means this is also 5, that distance there. So we've got an equilateral triangle. So the equilateral triangle will have a 60-degree angle, but in radians that is pi over 3. Okay, so what we can do here is we can work out this entire sector, which I'm going to shade in yellow, like this. So we can work out this sector. Okay, so the sector of a circle is equal to, and the formula in radians is a half r squared theta. So this is a half times by 5 is the radius squared, and theta is the angle made, which is pi over 3. Okay, great. So what's left to work out is this blue segment here, which incidentally is the same as, by symmetry, this segment here. Okay, now to work out the area of a segment, then what you'll need to do is you'll need to work out the area of the sector, which we already know, and then subtract the area of the triangle. Because if we have this whole yellow area, which we've already worked out, like so, if you subtract the area of the triangle from the yellow area, then you're left with that blue area, which is what we're looking for. So the segment is equal to the sector minus the triangle. Now we already know what the sector is. It's this thing here, which we can actually simplify to be 25 pi over 2 and 3 makes 6. So the sector is 25 pi over 6 minus the triangle. Now for the triangle we're going to use a half AB sine C. So as long as you have two sides with the angle in between them, then you can use that formula. So we do have two sides, we've got the 5 and the 5, and we've got the angle in between them. So it's going to be a half of A times B times by sine of C, which is the angle in between the two sides, like so. Okay, great, so that's 25 pi over 6 minus, and then that's 25 over 2. And sine of pi over 3 is sine of 60, which is root 3 over 2. Okay, great. So now to work out r, we need to take the whole semicircle, subtract the sector, which is the bit in yellow, and then subtract the segment, which is the bit in blue, and we'll be left with r. So r is equal to the semicircle minus the sector minus the segment, which will be, the semicircle is 25 over 2 pi, the sector is 25 pi over 6, or 25 over 6 pi, and then the segment is 25 pi over 6 minus this times this, which is 25 root 3 over 4. Okay, so perhaps I'm going to put this into our calculator. Okay, so I've just done the pi's separately because we need to give it as an exact form. So I've done this, this, and then I've minused this as well. So we're going to keep the pi separate, and that's going to give me 25 over 6 pi. And then this negative here and that negative is going to make a positive, so plus the 25 root 3 over 4. And I believe that is the form they want it in. I can just see it at the top there, and it is 25 over 4 root 3, and then plus a certain number of pi's, which is 25 over 6 pi. Yeah, so that's exactly the same. That's perfect. Okay, job done. Question 12. First off, we've got express 140 cos theta minus 480 sine theta in the form of r cos theta plus alpha. Okay, so my little hack for this is, because we are converting into cos, my coefficient a is going to be whatever the cos coefficient is. So I'm going to call that one a. Because we're going into cos, I'm going to call the cos one a. If it was the other way around, well then I would call the sine one a. And then here, the sine coefficient is going to be our b value. Okay, once we know that, it's really simple. So we can just follow this procedure. So we've said that a is equal to 140, b is equal to 480, then r will always be the square root of a squared plus b squared, which is the square root of 140 squared plus 480 squared, which can just go into our calculator. Voila. Oh, 500. Oh, nice. Okay. And then the alpha is always equal to tan to the minus 1 of b over a. So we're just going to go tan to the minus 1. Now, not in radians actually. It needs to be in degrees for this question. So changing into degrees. It's a bit of a faff on this calculator, to be honest. But hey ho, got to get with the times. Okay, so to the minus 1 of 480 over 140. Okay, great. So that was 480 over 140, and that gave us 73.7. Okay, to 2 decimal places, so that is 74. Okay, now the question does say express that in the form. So I'm just going to do one final thing, which is by saying 140 cos theta plus 480 sine theta is equal to 500 cos theta plus 73.74. And that is expressed in that form, so definitely getting the marks. Perfect. Okay. A scientist studies the number of rabbits and the number of foxes in a wood for 1 year. The number of rabbits R is modelled by this equation. Okay, so it says find a complete equation for the model given that the maximum number of rabbits in the wood is equal to 1,500. And really importantly, it's the number of rabbits, so okay, each number is worth 1 rabbit, and time is given in months, so that's something to remember as well. Okay, so let's write out the equation here. So this equation for R, we're going to write it out, but we're going to use obviously the R cos theta plus alpha that we've already found. Okay, so writing out that equation, this is going to give us that R is equal to A plus 500 cos, and the theta was 30t, plus 73.74. Now the maximum that a cos function can be is 1. So if we are looking at R max, which we're told is 1500, then that will equal A plus 500 multiplied by 1, because this yellow bit, the biggest it could possibly be is 1, and if we want to maximise, then we're going to have to use 1. So this clearly means that A must equal 1000. So A is 1000, but it does say find a complete equation for this model. So I need to write the actual equation out. So the equation would be R is equal to 1000 plus 500 cos of 30t plus 73.74. Okay, so that is the equation in full. We need to write that out if it asks for the complete equation. Okay, the next part is write down the minimum number of rabbits in the wood according to this model. Okay, so let's think again about that yellow cos function. The maximum it could have been was 1, and the minimum a cos function can be is -1. So if we are looking for our minimum, then that will be, using this equation here, it will be 1000 plus 500 times by the smallest that the yellow cos function can be, which is -1. So this is clearly going to give us just 500. Okay, and we don't need to put the units in there because it does just say the number of rabbits, of which 500 is the number of rabbits. Okay, so the actual number of rabbits in the wood is at a minimum value in the middle of April. Use this information to comment on the model for the number of rabbits. Well, time is in months. So what would T be if we were in the middle of April, given that T is in months and it is the time after the start of the year? Right, so I would definitely have to write this down myself, but if T was 1, then it's 1 month after the start of the year, so that would be like the end of January, or like literally the first day of February, one of the two. So if t is equal to 2, then that would be right at the end of February. T is equal to 3 will be the end of March. And if t was equal to 4, that would be right at the end of April. But we want halfway through April, which is halfway between these two. So halfway through April, t would equal 3.5, which is what we want. Okay, so we just need to sub in t is 3.5 into our formula. So we can say that r is equal to 1000 plus 500 cos of 30 times 3.5 plus 73.74. That's going to go into the calculator. Okay, so just put that in, and this is giving us that r is equal to 500.12. Given that r is the number of rabbits, then this is approximately 500, because the model is obviously modelling discrete data, because it's literally the number of rabbits. You can't have like half a rabbit. So use this information to comment, and it says that at that point it is at the minimum value, and the minimum value was 500, and we've got 500, so we're going to say that this is an effective model. So we can say that given the value from the model is very accurate, we can say the model is good. And that should do the job. Okay, we carry on. So we've now got number of foxes in the wood during the same year is modelled by this equation, which is different. The number of foxes is at its minimum value after t months. So minimum after t months. Find, according to the model, the number of rabbits in bold in the wood at the time t months. Okay, so we need to minimize this, find the time which minimizes it, and then substitute that time back into the rabbits formula. Okay. Alright, so to minimize this, we're going to say fmin. In the same token as what we said before, sine and cos, they both fluctuate between 1 and -1. So to minimize this, we want that sine function here to equal -1. So in fact, if we have a fmin, all we need to know really is that this sine function is equal to -1, because that's what's going to minimize f. So we can then just solve this equation to find the t value, which will then substitute back into the rabbit formula. Okay, so 30t plus 70. Well, inverse sine of -1 in degrees will give us -90, which isn't very helpful. So we're going to need to find the second solution for sine, and hopefully you know all your second solution formulas. And for sine, the second solution is 180 minus the first solution. Just incidentally, cos is 360 minus, and tan is 180 plus. So always good to know those, because we're going to need a second solution here, because if we solve this for t, it's going to give us a negative number. So the second solution, 180 minus -90, is 270. And that is going to give us a positive time, which is good. So 30t, we're going to subtract 70 from 270. We're going to ignore this one to give us 200. So the t value we're looking for is 200 over 30, which is the same as 20 over 3. Okay, now that needs to go back into the rabbit formula. And here is said rabbit formula. So we do 1000 plus cos of 30 multiplied by 20 over 3 plus 73.74, and that will go into our calculator. Okay, this gives us 1032.6, which is approximately, given it's a number of rabbits, we need to have a whole number. So we're going to round that up to 1033 rabbits. And that will complete that question. Okay, question 13, and we've got a is a positive constant. Use the substitution x is equal to a sine squared theta to show that. Okay, so with any substitution, we're going to start off by writing it out and then differentiating it. Now, in order to differentiate sine squared, we're going to have to use the chain rule. So in order to do that, we might write this as a sine squared theta, and then we write dx by d theta. And the way that we use the chain rule, if we have a bracket like this to a power, is we bring the power down to the front, we keep the bracket exactly the same, we drop the power down by 1, just like we're differentiating something, and then, and crucially, we multiply by the derivative of the bracket, and that is cos theta, because sine differentiates to cos theta. So this is the same as 2a sine theta cos theta, and if you know your double angle formulas, then you'll know that 2 sine theta cos theta is the same as sine 2 theta. There's an a there as well, so it's a sine 2 theta. So then in order to get dx, we just multiply both sides by d theta, so it's a sine 2 theta d theta. Okay, right, we'll bag that up because we're going to use that for sure. And then we're going to look at the limits next. So these limits are in terms of x, but if we are going to substitute x out for the variable theta, we need to write the limits now in terms of theta. So we've got x is equal to a, which is this one here. We also know that x is equal to a sine squared theta. Okay, so let's solve to find the theta value, which is going to give us this limit. So dividing both sides by a gives us 1 is equal to sine squared theta, and then square rooting. Over 2. Okay, perfect. And then next we are going to look at this one where x is 0. So we're going to say x is equal to 0, which is equal to a sine squared theta. Divide by a and square root, we're going to get 0 is equal to sine theta, which tells us that theta must be equal to 0 because sine theta is 0 when theta is 0. Okay, so those are our two limits sorted, and they're actually given here, but we need to show it all, so we've done that nice and effectively. So now it's just a case really, given that we've already done dx, we've got that sorted, we've got our limits sorted, so now it's just a case of looking at the actual integrand, which is the bit inside the integral sign. So this one is the square root of x, so I'll just write that down here. X to the power of a half is obviously the square root of x, which is equal to the square root of a sine squared theta, which we could write as square root a times by sine theta. Because these two things are multiplied together using surd rules, we can split it up and square root each part separately. Okay, right, I think we're good to go now. Okay, so we're going to say that it is the integral between the new limits, which is pi over 2 and 0, as we shown. And now this x to the power of a half we've said that's the same as root A sine theta, and then we've got the square root of A minus x, and x is the substitution A sine squared theta, and then dx is what's given up here, which is A sine 2 theta d theta. Okay, so what we're going to do next is we're going to pull out an A from this bracket here. So this square root, we can imagine it as a bracket. So it's a bracket to the power of a half, because that's what square root is. So if we could take out a factor of A, but if you take out a factor of A, you have to take out the power as well, which is a half, so you have to take out the square root of A. And that will leave 1 minus sine squared theta. So we just split up this third essentially as A and 1 minus sine squared. Okay, so let's just write that out as well. Oops, that should be pi over 2. Okay, so pi over 2 and 0, and then yeah, I think we're good to go here actually, because what's this times by an A? Well, root A times root A is A times by another A is A squared. We have sine theta here, and then 1 minus sine squared, as we should know from our identities. Well, we know that cos squared theta plus sine squared theta is equal to 1, so 1 minus sine squared theta is equal to cos squared theta. So if this is cos squared under the square root, if we square root it, we get cos theta. So that's cos theta, and then we've still got this sine 2 theta here, d theta. Okay, great. Well, what is this? Sine theta times cos theta. Well, we've already shown earlier that, or not shown it, but we know that our double angle formula, sine 2 theta, is 2 sine theta cos theta. So dividing both sides by 2, we get a half of sine 2 theta is equal to sine theta cos theta, which is what we have right here. So this means we have between pi over 2 and 0, we have a squared multiplied by a half sine 2 theta times by another sine 2 theta d theta. Okay, so because this is a show that question, I want to just make sure I get all these marks. And yeah, I think we're good now. So what we could do is we could just take out the constants, of which we have a half and we have a squared, like so. And then inside we've got sine 2 theta and a sine 2 theta multiplied together, which gives us sine squared 2 theta d theta. And I believe that is as required. Perfect. Okay, part B just says use algebraic integration to show that the integral which we have rearranged is equal to k pi a squared. So we're just going to integrate this basically. Okay, so how do you integrate a sine squared? Well, for a sine squared, you have to use the double angle formula for cos 2 theta. Because cos 2 theta, as we know, is equal to quite a lot of things actually. It's equal to cos squared theta minus sine squared theta. Or you can rewrite that as cos squared theta minus 2 cos squared theta minus 1. Or you can rewrite that as 1 minus 2 sine squared theta. So this is the one we're going to use. But this gives us, well, this will eventually give us an expression for sine squared, but we want to level this up because we want sine 2 theta squared. So we're just going to double the input here. So we're going to turn this theta into a 2 theta, which is going to turn this 2 theta into a 4 theta. So we're going to say cos 4 theta is 1 minus 2 sine squared 2 theta. Now we're going to rearrange this by adding this sine squared 2 theta to this side and subtracting this cos 4 theta to that side. And then we're going to divide by 2 on both sides to get a half 1 minus cos 4 theta. So that is going to replace this sine squared 2 theta. So for part B, this integral here is going to become a half a squared between 0 between pi over 2 and 0 of a half of 1 minus cos 4 theta d theta. Now this is a constant, a half, so we can, it's a factor of the integrand, so we can take that out like that. So just take out a half and times it by the half there to get a quarter. And now we can integrate 1 minus cos 4 theta d theta. And that will give us, well, 1 is going to integrate to theta with respect to theta. Cos 4 theta, so minus cos 4 theta is going to integrate to minus sine 4 theta, but the input here of 4 theta, we need to divide by the derivative of that. So it's going to be a fourth of sine 4 theta. Because minus cos integrates to minus sine. And again, yes, the input is 4 theta, so we're going to divide by the derivative of 4 theta, which is 4. Okay, and then now we're going to need to sub these limits in. Okay, which should actually be relatively straightforward, actually, because when we sub in pi over 2, we get pi over 2, and pi over 2 times by 4 is 2 pi, and sine of 2 pi is 0. So we get minus 0. And then when we sub in 0, we get 0, and sine of 0 is 0. So that's great. So it looks to me like we just have pi over 2 times by the constant outside, which is going to give us 1/8 a squared pi for our final answer. Perfect. Question 14. A balloon is being inflated. In this simple model, the balloon is modelled as a sphere, and the rate of increase of the radius of the balloon is inverse proportional to the square root of the radius of the balloon. Easy for you to say. Okay, at t seconds, the radius of the balloon is r. Write down a differential equation to model this solution. Okay, well that's not a lot to go on, is it? But I think the key point here is that the rate of increase of radius is inversely proportional to the square root of the radius of the balloon. That's what we need to use. So the rate of increase of the radius means dr by dt, how the radius is changing with respect to time. And that's inversely proportional, so it's proportional to 1 over, because it's inversely, the square root of the radius, so the root of the radius. Okay, so now we have that, we can say that dr by dt is equal to a constant multiplied by 1 over the square root of r, so we can write it as k over root r. Now that, by my book, is a differential equation. So that's it. 1 mark in the bag. Okay, the next part says at the instant when t is equal to 10, we have the radius is 16 and the radius is increasing at a rate of 1.9 centimeters per second. Okay, just double check that the units are in seconds, maybe very sneaky, and r is in centimeters. Yeah, if they were to pull a fast one there, but you never know. Always double check the units before you start. Okay, so solve the differential equation. Okay, so we're going to do the good old separation of variables here. So we're going to multiply. We're just going to cross multiply like that, you know. So we're going to have a root r, which is the same as r to the half. Dr is equal to k dt. And once we've done that, we integrate both sides. Okay, great. So integrate, we up the power and we divide by the new power, which is the same as timesing by 2/3. And that's going to equal k integrated, or k is a constant, with respect to t, means it's going to integrate to kt, and then plus c for the constant of integration, which you don't need to put on both sides. You just need one constant of integration, that will suffice. Okay, so we've got two constants that we need to find, k and c. We're going to need two bits of information. And those bits of information are that when t is equal to 10, r is equal to 16. So when t is equal to 10, we have r is equal to 16. So we'll put that in first. And this is going to give us 2/3 of 16 to the power of 3/2 is equal to, t is 10, so that's 10k plus c. Okay, 16 to the 3/2, well, 16 rooted is 4, and then cubed is 64, times by 2 is 128. So 128/3 is equal to 10k plus c. Right, we can't go any further with that because there's two constants there, so we're not going to be able to solve that. So we're looking like a simultaneous equation, and we need to use the other bit of information, which is the radius is increasing at a rate. So that means we need to, if it's increasing at a rate, that means we need to look at the derivative, which we have here. So we're going to substitute into that formula in order to find k. So the radius is increasing, and that is at when t is equal to 10 and when r is equal to 16. This is all happening. So r is 16 when the dr by dt is 0.9. So using the purple formula, the dr by dt is 0.9, and that happens when r is 16, like so. So what we're going to do here, well, root 16 is 4, so times both sides by 4 gives us 3.6 is equal to k, like so. Okay, brilliant. So that is one of the constants. And now we're going to use this equation to find the other one. Okay, so we can say that 128/3 is equal to 10, and k we know is 3.6 plus c. Therefore, this is going to give us a value of c. So just using the calculator to rearrange that equation to solve for c, to get 20/3. Okay, so we've got the two constants, and now we just need to put it back into the equation. This was the equation. Okay, so we can see it at the top there. So it's just going to be 2. It's going to be 2/3 r to the 3/2 is equal to k t plus c. And if we go up to the top here, we can see that we are looking for this to be on its own. So we need to multiply each, or divide each term by 2/3. And in doing so, we get 5.4 here if we divide this by 2/3. And if we divide this by 2/3, we get 10. And that is the equation that we are meant to show. So that is as required. Okay. So part C says, hence find the radius of the balloon when t is equal to 20. Give your answer to the nearest millimetre. Millimetre, that's cheeky because we're in centimetres here. As you can see, I've highlighted centimetres. Okay, so we just need to sub in t is equal to 20 and solve for r. Okay, so part C, we are subbing in t is equal to 20 right into this one here. So this gives us 5.4 multiplied by 20 plus 10, which gives us 108 plus 10, so that's 118. Okay, so what we could do is we can take this and we can square both sides, and that will cancel out the half power there, so we get r cubed is equal to 118 squared. So then to get r, we're going to do the cube root of 118 squared. Okay, can't do that one in my head. And we get 24.06 roughly, that's centimeters. So they want that in millimeters, so I have to times through by 10 to get it into millimeters, and it's the nearest millimeter, so that is approximately 241 millimeters. Perfect. Okay, now on to the final part. D, suggest a limitation of the model. Well, you can see here this model that as time increases, this right hand side of the equation is just going to get larger and larger and larger and larger, which means that r is just going to get larger and larger indefinitely. So we can say that the model becomes invalid for large t as it predicts the balloon will increase in size indefinitely. Perfect. Okay, 15 point I says show that this is positive for all real values of k. Okay, right, I can do this one. We can complete the square. So we get k minus 2 because, well, to complete the square, hopefully you guys know how to do this, but it's all about the b term. You halve the b term, and half of minus 4 is minus 2. So you put in brackets k minus 2, all squared, and then you always subtract whatever the half of that b term is squared. And then we've also got 5 to add on. This gives k minus 2 squared minus 4 plus 5, and this gives k minus 2 squared plus 1. And then we can say that as k minus 2 squared is greater than or equal to 0 for all k, k minus 2 squared plus 1 is greater than 0 for all k. So we know this is because any square expression is always greater than or equal to 0. So that's, we don't have to prove that. That's a given. So when you add 1 to it, it's definitely going to be greater than 0 for all k. And then I'm just going to go say hence. So always want a conclusion statement, which is k squared minus 4k plus 5 is positive for all real values of k. For all k real. Brilliant. Okay, right, on to part 2. It says a student was asked to prove by contradiction that there are no positive integers x and y such that this bracket multiplied by that bracket is equal to 28, The start of the student proof is shown below, so that they've assumed the negation, which is what you should do for a proof by contradiction. And then they have solved the pairing of 14 and 2 and got no integers. Okay, so we need to do all the other pairings. Okay, right, so I'm here and I am going to list out all of the pairings. So 14 times 2 is the one that they have literally done. So but this bracket here is 14, that bracket there is 2. Now the other way round would be the first bracket being 2 and then the other one being 14. Or we could have 1 and 28, 28 and 1, 7 and 4, 4 and 7. Or we could have minus 14 and minus 2, minus 2 and minus 14, minus 1 times minus 28, minus 28 times minus 1, minus 7 times minus 4, or minus 4 times minus 7. So these are all of the integers that are going to multiply to make 28. And we know that they have to be integers because we are assuming that x and y are positive integers, so these brackets will therefore be integers. Okay, so we could check all of these pairings, do simultaneous equations for all of them, but there are some which we don't need to do. And the reason why is that the first bracket, so 3x plus 2y, is definitely positive. Because if x and y are positive integers, then we know that 3x plus 2y is going to be bigger than or equal to 5. 5 is the smallest it could possibly be. So then we can say, therefore, the equations that are equal to negative numbers are impossible. Okay, so there's no point us writing, for example, 3x plus 2y is equal to minus 14, and then 2x minus 5y is equal to minus 2, because we know that 3x plus 2y must be positive. So what we can do is we can then get rid of all the ones on the right hand side here. Those have been checked. Okay, they're never ever going to work. Also, because, oh yes, perfect, 3x plus 2y is definitely going to be bigger than 2x minus 5y, because 3x is bigger than 2x. Again, these are positive integers, so 3x is definitely bigger than 2x. And you're adding 2y on this side, but you're taking away 5y on that side. So this one is definitely bigger. So that means, therefore, equations where 3x plus 2y is going to be greater than the 2x minus, where this one is less than, can be impossible. Are impossible. So it means we can get rid of this one, because again this left number represents the left bracket and we need that one to be bigger. Get rid of that one and this one. So in fact it's just these two that we need to check. So let's do that. Let's do 3x plus 2y is equal to 28 and 2x minus 5y is equal to 1. So we can do that on our calculator. We can go to equation, simultaneous, two unknowns. We can do 3 to 28 to minus 5 and 1. Okay, great. And we get x equals 142 over 19, and y equals 53 over 19, and these are not integers. Okay, great. So the other one that we need to do, we can just go back, and we can change it up. We could change this for 7, and then we can change this for 4. Okay, great. And we have to write that out. So we'll write 3x plus 2y equals 7, and 2x minus 5y is equal to 4. And we get here x is equal to 43 over 19, and y is equal to 2 over 19. So these are not integers. Perfect. So that means that we have now checked all possible cases. So we can say that we have checked all cases and found that all are impossible. Therefore, the statement is proved to be true. Brilliant. Right, I hope you enjoyed that. Subscribe to my YouTube channel. I'm trying to get to 100k, so it'd be great if you can help out and click that subscribe button, and I'll see you in the next one. Bye for now.